function forwards, and we translate one of them, and we integrate them together, and we call it the convolution. This is the same thing as the integral from 0 to t of f alpha g of t minus alpha. So that is to say that it doesn't matter in what order we do it, right? That the convolution of f against g will be the same thing as the convolution of g against f. Do you want? Is that obvious that these things are equal? Shannon.
Yes, I was just asking about the asterisk. Does that represent convoluting?
Yeah.
Okay.
The asterisk is the symbol for convolution.
Just make sure.
So it's commutative that f star g equals g star f?
That's right.
Okay.
That's right. So so it turns out that convolution has some properties. One, doesn't matter in which order you convolve. Two, it's also true that if you convolve two functions and then convolve them against a third, then it's the same thing as convolving one function against the convolution of the other two functions. F convolved with a distributive property. If you convolve against a sum, well, that's the same thing as the sum of the convolutions. And number 4, obviously, if you convolve with 0, you get the 0 function. Okay, so this should, what does this remind you of? Well, does this remind you of anything? Like, what does convolution strike you to be similar to?
Multiplication.
Multiplication, right? It's some way of multiplying functions, right? And it turns out to be commutative, associative. It has a 0, right? You multiply by 0, you get 0. So you can think of it as sort of putting a multiplication, a natural multiplication on functions, right? Just like numbers have multiplication, the functions can be made into something with a similar structure. Something with a similar structure by using this thing convolution. In fact, it turns. If you do it properly, it turns into something called an algebra or a Banach algebra. If you know Professor Grabner down in Pomona, this is all he thinks about Banach algebras.
Is a convolution an order? Because like multiplication and integers is order. Like,
is there
some ordering scheme to this multiplication?
So you're asking if there's some order that's compatible with the convolution. No, right? Because that is how you have to put an order on the functions, right? And so unless you no. Right? How would you put an order on the space of functions? You can put some sort of partial order on it, but not a total. But this sort of gives rise to one question, which is, what's the obvious question you think of when you see this thing? Well, you've got multiplication, you've got commutative property, you've got distributive property, you've got associative property, you convolve with 0, blah, blah, blah. What would you hope for? Some sort of identity, right? You want to convolve with something and get yourself back, right? And maybe even better, you want inverses then. Right? If there is an identity, assuming that there is some sort of thing called the identity, well then you want to be able to deconvolve, right? Suppose you convolve with some function, you want to deconvolve, right? And get rid of convolution. And in fact, this is what is done when people are using sonar, say. As I recall, it's the people in the military really try to do something like deconvolution, right? To figure out what actually is on the other side, right? So you get all this, you send your sonar out, you get all this data back. The data you get is actually a convolution of the reality with the signal that you sent out. Okay, and so you want to be able to deconvolve and get an accurate picture of what is out there. Okay. So that's one very serious application of convolution. Okay, so so maybe you can guess, what is the identity? What should the identity be?
With 1?
Well, let's see. If we convolve with 1, right, then we're going to get the integral from 0 to t of f of t minus alpha 1 d alpha, right? So we're going to get the integral of the function, right? So that's not, is that the same thing as f of t? No, not really, right? It's not 1. Convolving with 1 does you no good. But, anyone guess? I'll give you 5 seconds. 1.
Can you use the antiderivative some way?
What?
Can you use the antiderivative some way? The antiderivative in some way? I don't know.
4.
No.
Is the Dirac delta function is the it's the Dirac delta, right? Because you look what happens, right? If you convolve with the Dirac delta function, if it existed, right? Convolve with the Dirac delta function, what is it going to do for you? Well, 0 to t, f of t minus alpha, Dirac delta function, right? Alpha, d alpha, right? That's going to pick off the value when alpha is equal to 0, right? The value when alpha is equal to 0. When alpha is equal to 0, that's going to be f of t, right? And that'll be f of t, right? So convolving with the Dirac delta function just gives you that function. And so this is part of the trouble of convolution, right, or deconvolution, because the identity is the Dirac delta function. Yeah.
Did you show how like exactly that happens? Or explain that again?
Remember what the Dirac delta function does, right? It kicks off, it says, I'm going to ignore everything except when alpha is equal to 0, right? And at alpha equals 0, I'm going to integrate to 1. Okay? So when unless alpha is equal to 0, you just ignore everything except alpha equal to 0, right? So this is going to be the integral of 0 to 0 f of t minus alpha. This, right? This, when alpha is equal to 0, is f of t, right? And so you get f of t times 1, right? F of t times 1. Or if you want, you can do it the long way and use the t times, but I'm just...
So how does the integral from 0 to t become 0 to 0?
Because the delta function ignores everything except when alpha is equal to 0. Remember, delta is going to be 0 everywhere except when alpha is 0. Right? So it doesn't care. It doesn't care what the value of f is outside of there. Okay. I don't think I have time to do it, but let me.
So you just write you need like a limit before the integral, or is it actually like the integral from 0 to 0 d alpha?
So to do it properly, yes, you need to go through the details, but
Okay.
yeah. Okay. So let me at least state this theorem. So here's why we're interested in convolution. So for good f and g, if the Laplace transforms exist, if LF and LG exist for s bigger than a, then the Laplace transform of convolution is the product of the Laplace transforms. takes convolution and turns it into multiplication. Okay, or said conversely, right, if you're taking the inverse Laplace transform of a product, right, what are you going to get? You're going to get the functions, you're going to get the convolution of the functions. Right? So, right, so whenever we see a product of things on the Laplace transform side, it actually turns into a convolution back here. Okay. And that will actually be a pretty powerful tool for extending the dictionary. I guess we'll do it on Friday.